In this clip, I'll be talking about the differentiability of piecewise defined functions at the seam line using two different methods. Sometimes piecewise defined functions are called split functions. And seam line is an informal word, sometimes also seam point, and it's the place where the function changes formula. You'll see in the example. I'll be teaching this concept through the use of a single example, which will follow us all the way through. And this example will be as follows. F of x is equal to, you see the split, x squared plus 8x whenever x is bigger or equal to 2, and x cubed plus 12 whenever x is less than 2. The first method will be using the definition of a derivative, and the second method will be using a theorem. And at the end, I'll say a few words about when to use which. I mean, when to use each of these methods for finding the differentiability. I'm going to start by showing method 1, and it's probably best to start on a new page. Recall that method 1 is using the definition of the derivative. What this says is as follows. If you want to check differentiability to point x equals a, which is a seam line, then we compute two quantities. The first is called the right derivative and is written with a little plus here and is defined as the limit as h goes to 0 from the right of f of a plus h minus f of a all over h. And the second quantity we compute is the left derivative, and this is the limit as h goes to 0 from the left of f of a plus h minus f of a over h. Now, if these two are equal, I mean the right derivative and the left derivative, then f is differentiable at x equals a. Otherwise not, by which I mean it's not differentiable otherwise. There's something I have to stress here, may not be obvious. When I say that these limits are equal, I mean that they're also finite, not infinite. What I need are finite limits. So please remember that infinity does not equal infinity necessarily. Infinity is out. And now it's time for our example using our function, and I'll do it on a fresh page. So here's our function as from before, and the seam line is 2, and that's where we want to check differentiability. So according to what I wrote, we first of all have to check the right derivative, which is called the derivative with a little plus here at the point 2, and this equals, according to the definition, to the limit as h goes to 0 of f of 2 plus h minus f of 2 over h. H goes to 0 from the right, of course, and then we continue. This equals the limit as h goes to 0 again from the right. Now, the question is what to use for f. Well, 2 plus h is slightly bigger than 2 because h is slightly positive. And so we're using this definition, which is x squared plus 8x. In other words, we get 2 plus h squared plus 8 times 2 plus h minus. Now, as for 2, it certainly belongs here. So we also use 2 squared plus 8 times 2 over h. And let's use the same coloring. And we'll continue with the algebra. So what do we get? Limit h goes to 0 plus. The square of this is 4 plus 4h plus h squared, and from here plus 16 plus 8h minus, this whole thing is 20, all over h, which equals limit, same thing. If we combine terms together, 4 and 16 is 20 minus 20, that cancels, and all we're left with is 4h plus 8h, which is 12h, and plus h squared, all over h, which we can cancel from top and bottom and get limit as h goes to 0 plus. Now 12h over h is just 12, and all we're left with is plus h, and when h goes to 0, this expression just goes to 12. So we got the limit from the right is 12. Let's see what happens with the limit from the left and see if they're equal or not. So here I've written our function again, and this time we're going to find the left derivative, which we write as f prime with a little minus here, again at the point 2, and what this is equal to is just like before, except that h goes to 0 from the left, the same thing, f of 2 plus h minus f of 2 over h, which equals the limit as h goes to 0 from the left. This time f might go from a different definition. We can't be sure it's the top one again. In fact, it's not, it's the bottom one, because h is slightly negative, so 2 plus h is slightly below 2, so we're going to use this definition, which means that what we have is 2 plus h to the power of 3 plus 12. This is the f of 2 plus h. F of 2, just like before, we computed it as 20, so it remains 20. And all this is over h. You might have forgotten the formula for a binomial cubed. A plus b to the power of 3 equals a cubed plus 3a squared b plus 3a b squared plus b cubed. And if we use that here, then we'll get, I'll spare you all the minor details, 8 plus 6 h plus plus 12h plus 6h squared plus h cubed plus 12 minus 20 all over h, which equals, the 8 goes with the 12 and the 20, and if we take h out, we get the limit as h goes to 0 from the left. H will cancel into all of these things, and we'll just get 12 plus 6h plus h squared. And as h goes to 0, these two terms go to 0, and all we're left with is 12. And this is very good, because what we got previously for the right derivative was also 12, and since 12 equals 12, then f is indeed differentiable. And that's not the only thing we can say. We can even say that we know what the derivative is, because the derivative of f at 2 is now this same value of the 12 from the left and 12 from the right, so this is also equal 12. As a matter of fact, there's something else interesting. I could actually show you a formula for the complete derivative of f. Just let me make some room by erasing some of this stuff. And then I can show you that we could make a split function for f prime and get that f prime of x equals, there was never any problem outside of the seam line x equals 2. So for x bigger than 2, we just differentiate regular and get from this 2x plus 8. This will be for x bigger than 2. And there was also no doubt that for x less than 2, this thing is differentiable as usual with the formula. 3x squared is all we get here. The only thing we had a problem with was 2 itself, and that we found was 12. And funnily, or not funnily, it turns out to be equal to both of these when x is 2, so we can pick. But since this was in this form, I'll put the equal sign over here. So here we have a nice formula for the derivative. Last thing I want to do is just summarize what we said here. So to summarize, since the right derivative at 2 equals the left derivative at 2, and if I remember this was equal to 12, then f is differentiable at x equals 2, and furthermore, the derivative of f at 2 is this common value of 12. Now we come to method 2 for differentiability, using a theorem. What is this theorem? Well, let me present it to you. It says, if f is continuous at x equals a, and the limit as x goes to a from the right of f prime of x, and limit as x goes to a from the left of f prime of x exist, both of them, and they're equal to each other. And this also implies that they're not infinity, they exist and they're finite. If these two conditions hold, then what we get is that f is differentiable at the point x equals a. And not only that, but we actually know the value of the derivative at a, which is equal to these two limits above that were already equal.